Hey folks, this question is recently asked by Amazon and Microsoft. We're given an n times n matrix and we need to return all the elements in the spiral order. The spiral order always has the following. First, it goes to the right, and then down, left, and then up, and then right. And we need to return the values that we visited in the spiral order. So no matter how your matrix looks like, it's like you're drawing the circle until you reach to the last element. I'm going to talk about the slicing feature in Python. First, let's get rid of the first row. In Python, you can call the function that matrix.pop at index 0. So it will result into the matrix like this. Next, I'm going to rotate the matrix. So if I keep slicing by popping the first row, and it will result into, I rotate again, and I pop the first row. So you can see it's actually following the spiral order. Now the tricky part is, how are we doing the rotate based on the matrix? In Python, we can call the zip function. If we are given two arrays here, then the zip function will link the element based on the index. So at index 0, it will link 4 and 7. At index 1, it will link 5 and 8. And then it will link 6 and 9. So this will result into... So this is the way we rotate clockwise here. But we need to rotate counterclockwise. So that means we need to reverse the matrix. You can call the column -1 to reverse the matrix. And this is the Python code. It is very short and neat. Notice that I put a star sign over here. This is to unpack the matrix into multiple lists. Because the zip function requires multiple lists in order to do the mapping. If you're trying to find the pattern of spiral order, it always performs this for operation in this order by n times until it visits all the nodes. So you can have the array that's called actions that stored all these 4 different operations. So you continue to loop through the actions until you visit all the nodes. The length of the matrix means the number of the rows, and the length of the matrix at index 0, that means the number of columns. So if these two times together, we can have the number of nodes. Therefore, if the length of the result is equal to the number of the rows, that means we already visit all of them, and we break the while loop. And this is the Python code that you can define for each action. You need to make sure that the movement is within the matrix boundary. For example, if you are moving to the right, you need to make sure the column is less than the number of the columns. And also need to ensure that the nodes are not visited before. Notice that if I finish the move to the right, I hit the boundary on here. Because of the while statement, my row and column is actually outside of the boundary. So I need to move the column back. That's the reason I have columns -1 here. And the reason I have row +1 here is that I just need to return the next point of the movement so that I can, starting from here, I can move down. Next, I'm going to talk about the other approach. Every time we are talking about from one point that we move to the other point, we can always think about the recursion. So in the recursion tree, if we put the actions in the spiral order, that is, first go to the right, down, left, and up, and we perform the depth first search, you can find out that the recursion tree is actually following the spiral order. So I denote RC as the name of the recursion function. The first parameter is the row index, and the second parameter is the column index. And you can see how the recursion works. So from the recursion tree, first it starts from 0, 0 and goes to the right until it reaches to 0, 2, which is on here. When it tries to go to the right again to 0, 3, we know that it reaches to outside of the boundary. And we return nothing to the parent's recursion because the second order, the second action is that we are going down. So we reach to 1, 2 over here. Now from 1, 2, because the order, right, we try to go to the right again. But 1, 3 is outside of the boundary, so it returns back, and this returns nothing. To the 1, 2 again, so we are trying to go down. 2, 2, this is valid. So for every recursion, if this is outside of the boundary, or we have been visited the nodes before, we just return to the parent's recursion and we do nothing. Otherwise, we keep going down. So from the spiral order, we know that the last node is on 1, 1 over here. So when when we are on 1, we try to reach to the other 4 nodes, and we know that these 4 nodes over here, they already been visited before. So we just return back, and then we back to the root. And this is the Python code. It is very straightforward and easy to understand. But one thing to keep that in mind is that, let's say if I go in the spiral order like this, and then I reach to number 9 here. From the recursion order, usually it goes to the right first, right, instead of going up. So I have the if statement here that says the column +1 is greater or equal to the row. So that means we are reaching to the node 5 here instead of node 9. So we can go to the right. And in order to save the space complexity, I mark the visit node as the number sign. So every time I just need to check if the value is equal to the number sign. If it is, that means we visited these nodes before, so I just return nothing. Based on the height of the recursion tree, that means m times n. N is the number of rows and n means the number of columns. So the time complexity is O m times n, which is acceptable.